Ladies and gentlemen, good morning, and thank you, Dominic, for inviting me here to share some gemmology with you. I'm going to have a look at different aspects of gemmology, from very elementary, basic, to more recent developments. And we start off in the year 1904. That's 1904. And here at the World Fair in St. Louis was this remarkable looking stone with the claim the largest and finest topaz in the world. Well, I had the chance to look at this some decades ago, and it was a citrine, a quartz, in fact. It was a citrine from the quartz family and not a topaz. But then in the year 1904, up until then, they did not have a refractometer. And then came the earliest refractometer that was commercially useful to adapt to gemstones, and that was developed by Herbert Smith. And this is my own instrument here that you see, very small, primitive looking, and interestingly, it could only measure up to refractive index 1.6 because it used monobromonaphthalene as the contact liquid. So it was very restrictive indeed. It couldn't look at sapphire. It couldn't look at many stones that were higher in refraction than 1.6. So very limited. And today we're spoiled because we have wonderful refractometers today. And you could see one here. We have an ICOST instrument here. I bought my ICOST refractometer in 1976. I still use it today. I've taught with it with students. It still has a very good prism surface today. It stood the test of time, and that's important because many refractometers used a soft prism or a brittle prism that easily splintered, and so it is important to have one with a very strong glass prism. When you look at a refractometer as a student, you're sometimes puzzled by some of the things that you see. On the left here, I've put a refractometer liquid on the refractometer, 1.81, but there's nothing to see. And then we put the gemstone on, and in this case, there doesn't seem to be anything at all to see. There's a little bit of shadow near the bottom, but we can't really make head nor tail of this. What is this telling us? This is because we're using lighting through the back of the instrument. If we use the light through the top of the instrument, as here, then suddenly the scale has lit up with the color of the gemstone, in this case a blue cubic zirconia. But for those gemstones that are above 1.8, it can be quite puzzling because you're not sure if you're not seeing a shadow because there's just not one forming, or perhaps it's higher than the liquid. How do you know? But by using this top lighting with a fiber optic, you immediately see this is a stone with a refractive index above the liquid. Using that overhead lighting has its uses in different situations. I find that with very small gems, faceted gems, maybe 1.5 millimeter, it's very difficult to get a shadow. Even as here on the left, where you can actually touch the stone with a pencil, the top back of a pencil or your finger, and no shadow forms. That's because of the traditional lighting. But if you bring your lighting down on top, the shadow comes back to front. We get the shadow from the high reading down, and you can read off quite clearly here. This is the ordinary ray, 1.560, and then we turn the polarizer and we get the extraordinary ray, 1.563. 1563 ordinary ray, 1.560 extraordinary ray. We measure the birefringence, And we've got the whole story here, not just of an emerald, but in this case, a flux-grown synthetic emerald, and by using top lighting. These Mashishi beryls have been seen at Tucson for many years now. I've seen stands by Lowe of Brazil, who've had several thousand of these on his stand at one time. And so they are out there. And of course, they look like aquamarines in many ways. The color does not retain. It's not a fast color. It tends to fade. And what I've done here, they were all matching. I put the two of them on an electric bulb, a 100 watt bulb, and it paled in no time at all. So we do have to be careful because Mashishi beryls do fade. At the top here is a row of aquamarines, but here is one of these Mashishi beryls. Well, if you bear in mind that aquamarine can be greenish blue or blue, the colors can be at times quite similar for your eye to say, oh, this is a Mashishi beryl. So how could we tell that it is a Mashishi beryl? How could we tell simply? Well, first of all, the ordinary ray of an aquamarine is the colorless ray, the color that travels along the crystal. But if we look at the extraordinary ray, the color which is laterally across the crystal, we see the color. Now, if we put an aquamarine onto a refractometer and we use top lighting, then we see that the extraordinary ray is blue, the lower refractive index, 1.566. The higher index, the ordinary ray, is colorless, 1.572. If you put a Mashishi beryl on your refractometer, it is the opposite. The lower reading becomes colorless and the higher reading becomes blue. At the same time, it enables you to say which ray carries which color. In this case, the blue is coming from the extraordinary ray. Here we see it here in the crystal. And the ordinary ray is colorless. We can equate that because as we turn the polarizer, the shadow moves up and down to give us the refractive index against the color. And so we can say here that the 1.566, the extraordinary ray, carries the blue color. In the Mashishi beryl, it's the opposite way round. Now we can carry this forward to a biaxial stone. This is, of course, uniaxial, but if we look at biaxial stones, then the alexandrite is the ultimate, perhaps. And I'm always amused the way the jewelry trade gets so carried away with the idea of color change. Well, of course there's color change because you change the lighting. And some gems do it more than others, yes, and alexandrite does it quite profoundly. But for my appreciation of alexandrite, it's the trichroism that really is extraordinary. And you can see it here with the three rays, the alpha, beta, gamma. Now, if we put such a stone on our refractometer and use top lighting, then we can actually see where the colors come from. Because not only have we got our scale, this is an ICOST refractometer, we see the scale very clearly, but we see the scale has gone red, amber, greeny blue, because we're transmitting with the polarizer just one ray at a time, alpha, beta, gamma. At the same time, the shadow changes its position, 1.745, 1.753 is gamma, the highest reading, so we can actually say which color comes from which ray. I find this the student is helped by this to begin to understand where these colors are coming from, the pleochroic colors, how they relate to our refractive index. But by using top lighting, you can see this yourself quite clearly, quite simply. In the twinned alexandrite, the trilling as we call it, we can, with a piece of Polaroid or a polarizer, we can see the segments change their colors. As we turn the polarizer, the gamma here has become an alpha, and the alpha here has become a gamma, just by turning the polarizer as we look at the stone. That's natural, and they're wonderful to see, these crystals, the way the color is spread through the stone. But there are also twinned, multi-twinned synthetic alexandrites, and here we see one here, a Kyocera synthetic alexandrite, and we see the segments quite clearly here. We've got alpha, we've got beta, and we've got gamma. And in the one stone, because it's faceted on the back with the natural faces of the crystal, by reflection we're seeing all three colors at the same time, which is very unusual. Usually you only see two, the dichroic colors of a trichroic stone, but here we see the three. And if we look down the end of the stone through the edge, we can see alpha again, and here we see beta. So it's not just natural stones that are trillings. The alexandrite is seen sometimes twinned, cyclically twinned, and then you have these very wonderful color effects coming from the stone, natural or synthetic. And then the alexandrite cat's eye. These are not seen so often, but they are fascinating because, being an alexandrite, we do get a color change. And here we see the color changing from daylight to the red with the tungsten light of a hotter and incandescent lamp. It's interesting that there are chrysoberyl starstones, usually with a forearm, and it's interesting how you see a wide ray, a wide arm, and a narrow arm. I can find no record of a star alexandrite, but in 1962, Robert Crowningshield, writing in Gems and Gemmology, did speak of a star alexandrite. But when you look at the photograph, there was really only one arm, this one, and the other arm, it really had only you could just form, it didn't actually complete the form. So to call it a star alexandrite was really, I think, stretching the imagination too far. But certainly star chrysoberyl as here. Now these are natural stones, and this is not safe from the synthesizer either. As here we have synthetic cat's eyes or synthetic star stones, and it's interesting because it's a two-stage progression. The original crystal is grown, as here at the top, usually Zukralski, or pulling as it's termed. Zukralski is the first stage. Now, if they were making laser material, and this was all to do with technology, nothing to do with the jewelry trade, but when they attempted to take out the defects from the crystal, because a laser has to have no crystal defects, in the process here of this infrared radiation, it's called zone melting or zone refining or floating zone, the three terms used for this technique. You can see that the crystal is massaged. This crystal becomes massaged, it changes shape, and it ends up as a tube, like a cylinder, about 1 centimeter in diameter. Now in that process, because titanium was used in the growth of the synthetic, the titanium grouped together to become rutile, and we then got the cat's eye. And I remember when I gave this rod to my cutting friend and said, "Oh, will you cut me a cabochon?" And I looked forward to getting the cat's eye, and sure enough, I got a cat's eye alexandrite back. But there was only half the crystal used, and I said, "Well, cut me another one, but cut it at right angles to the first one, just for fun, really." And so the first one came out, it was the cat's eye, but when my cutter friend, Doug Morgan, cut the other one, here it was, a six-arm star synthetic alexandrite. I understand that the late Professor Bossart has another one as well, but I've not heard of this in any other literature, but I loaned these stones to Carl Schmetzer, Dr. Schmetzer, and recently articles in the Journal of Gemmology and the Australian Gemmologist have carried articles on these very stones, explaining how they come about and analysing the inclusions as, in fact, the rutile. But they're so fine, they are such fine inclusions that even using Raman, they're not positively able to say that it is rutile, but it is a titanium phase anyway. But there's the natural at the bottom. You can see the lovely cat's eye here. And then when we look by cross polars, it's awfully difficult to photograph these lines. They really are difficult to illuminate so you can see them clearly. But finally, I managed to produce a photograph that does show these effects. But these two top photos on left and right, they were by Dr. Schmetzer while he had the stones. But these other photographs are my own. And you can see here that in the synthetic, it's rather a cloudy sort of fibrous structure, whereas in the natural, it's a much sharper structure that produces the cat's eye, which explains perhaps why we've got such a sharp cat's eye in the natural, whereas it's more of a woolly stone here. Also, notice how this is more translucent, whereas translucent heading for opaque. The natural is more translucent, becoming almost transparent by comparison. Just a closer look now at the two of them that I've just shown. And Dr. Schmetzer has determined that these are needles or channels, which are negative crystals. They're so fine, it's even beyond the power of his examination to declare which they are. At the bottom here, we see the synthetic, and you can see how woolly it is in contrast to these very sharp striations in the natural cat's eye. Other things that are going to give us a much more positive answer to natural or synthetic, if you look at the back, you can see here a typical reverse, the underside of a cat's eye or a starstone, like a star sapphire, star ruby. If you look at the back, they're not going to polish it because it takes away from the weight and takes away from the price they will get. So it's generally left very rough. Whereas when you look at the natural, when you look at the synthetic, it's been polished because it's of no value to polish and make it look more attractive. Also, a look at it by ultraviolet light, you can see the natural here producing very poor ultraviolet fluorescence because of the chromium, whereas there's chromium in the synthetic producing a very nice, sharp red response. That's not positive gemmology, it's not 100% proof, but it is a pointer for us. If we look at the same sort of thing that's done to sapphire, it's interesting because when we think of the verni, which we all are familiar with, verni has the color round the outside where the main heat is. Whereas in zone refining, the heat concentrates in the middle, so the titanium migrates and the iron migrates in the middle, and we get the color as a core. But both of these produce curved structures. Now, is it verni or is it zone refined? Well, with zone refining, we see we know this from our studies, we know we get these Plato-Sandmeyer structures, but when we look at the Kyocera, we see a very interesting picture indeed. There's the core, there's that curved ribbing, but when we look on cross polars, we see that blue core through the middle there, but look at these interesting interference figures. There's just a touch of the uniaxial cross there, but look at these peculiar strain figures that have come about, very different from the Plato, from the verni growth. These aquamarine tones here are interesting. You've got natural on the left and a rarer saturated tone on the right. And then comes synthetic aquamarine. There's lots of this about at Tucson particularly. And you can see that quite considerable weight of material there. Now, how are we going to tell this from the natural when we've got such stones as this one with a lot of natural-looking inclusions in? These are little dendrites which show up on high magnification, and to our eye, or with the loupe, we're going to think, oh, this has got to be a natural aquamarine. It's got the refractive index is right, the spectrum is right with its 427 nanometer band. How can we tell? Well, if we go on to a horizontal microscope, we can see here in this Manfred Eichhorst unit, we can see there is dichroism, the ordinary ray, the extraordinary ray. Then if we shadow, we begin to see the structure appearing. Now, that's my attempt at shadowing using a black card. How could we do this even better? I hope you have a comb with you, gentlemen, to comb your hair, because if you use a comb, you actually get a very much better view of this by shadowing using the comb. You can see it in position here, and up has come, we've got this subgrain division, like a bifurcation of growth in parallel with the C-axis, and quite distinctive in all the beryls, all the synthetic beryls at least. By hydrothermal growth, they produce this particular pattern. Not only is there that subgrain boundary that we see here, it's like a bifurcation effect, but you also see there are pinacoidal developments. But be careful, because we see these on natural emerald and aquamarine as well. It's these bifurcations on the C-axis that give the game away. And my last part of my talk is to do with what happens on your refractometer. If you lift the stone, you will change the refractive index. And you can see here I've lifted it far away from the eyepiece, and here I've lifted near to the eyepiece, and we produce different refractive indices from one stone which has an RI of 1.727. Now, if you bear that in mind, there is a scam now which is well worth knowing about, and that is by taking a natural spinel and giving it 2 table facets. You can see here there's a spine across the table. So we've a difference here of about 1 degree. When you put that on the refractometer, instead of being singly refractive because it's spinel, it produces 2 readings, and they are exactly where the taphite readings are. So anybody trying to sell you a stone in Sri Lanka or outside a laboratory, of course, they're able to show you with a refractometer, this is a taphite and not a spinel. So do be careful of this taphite scam. And if you change the angle between the spine further, you can also reproduce the sapphirine. And you think you've actually got sapphirines by your refractometer readings. So do be careful of that. With a spinel, it should be easy enough with your spectroscope to see this difference. But it's very clever to think of such a means of changing your spinel to a taphite, and you get an awful lot more money for it, as you can imagine.
How often you've seen or Tucson or after Tucson or last few years these stones that are cut with this extra facet as an extra table angle? How often does it happen that you see such stones?
I have friends in Sri Lanka, and in communications I heard about this possibility, and I said, will you cut me one? A man called Karan Nayaka in Colombo, and he quickly produced, they were in the post so very quickly. You can do it yourself if you're a lapidary, if you have a lapidary friend, give them a spinel and say, give me just a slight change of 1 degree on the table facet is enough, because each angle produces its own refractive index. Thank you. A stone needs to sit flat on a refractometer and it gives you a true reading. But I showed you if you lift the stone, you change the refractive index. And by giving it 2 table facets, you produce 2 readings from each of the angles of the table facet. It's quite easy to do yourselves, but please don't blame me if you get into trouble for doing it.
Okay, thank you very much. appreciate you. Mr. Leung, I think you
Yes.
have
Thank you.
some
Thank you, Helen.
housekeeping news.
Yeah, thank you, Helen. Thank you. Yeah.